Thanks for the very generous introduction. And yeah, so it's going to be the last talk. So I decided to talk about two of my recently rejected papers. I'm pretty sure you have all heard about the accepted papers. So let's start with the first paper, which was rejected from ICML, and then is now currently under review at another conference that, according to the new policy, that I cannot really disclose. So the title is called Non-Auto-Regressive Neural Sequence Modeling, and then it's been done mainly by two of my PhD students, Jason Lee and Elman Mansimanov. So, in this summer school, I'm pretty sure you have learned a lot about how to do the sequence modeling, like starting with the HMMs, CRFs, and then a bit of a neural sequence modeling this morning. And neural sequence modeling is, in fact, if you think about it, it's a very straightforward problem. So we're going to have some kind of input that can be very arbitrary. It could be image, it could be another sequence, it could be video, it could be whatever really you want it to be. And then now our goal is to build a machine that's going to output some sequence given or that corresponds to the arbitrary input x. And then that problem can be written down as trying to estimating a distribution over all possible sequences given x. So we're going to train a neural net that's going to be parameterized by a set of parameters, theta, and then the neural net is going to take as the input, some input, and then estimate or outputs a distribution over all possible sequences. So this morning we learned about machine translation, and then that same technology can be used for the speech recognition and image caption generation, so on and so on. So what is the major difference between this kind of sequence model and the classification? In the classification, one of the biggest assumptions is that all the classes that you're going to try to assign the input to, all those classes are mutually independent from each other, conditioned on the input. On the other hand, in the sequence modeling, the output sequence has extremely strong dependencies among each other. So it's going to be a sequence of tokens, and then one token in the sequence is going to be extremely dependent on the other tokens. So for instance, let's take an example. If I start reading whatever the input there was, more than half of residents in Korea speak, then somehow you can all know that the answer is going to be Korean, even though you have absolutely no idea what the input is. It just tells us that we can, by looking at other tokens, get a very low entropy distribution over the unknown tokens. And often what we do is, in order to capture these strong dependencies, temporal dependencies, we use a auto-regressive sequence modeling. That is, we're going to say that the probability of one token in the output is going to be dependent on all the previous tokens as well as the input. So in this specific case, in order to tell what the final token is going to be, we need to look not only at the input, but also all the previous tokens. And then by just looking at all the previous tokens, we can really easily tell what the token is going to be. So the generative story is really nice. We're going to start from the sum, let's say beginning of sentence, some special token, trying to sample the first word, let's say it. And then given those two, we are going to try to sample the next token, let's say explicitly. And then given all of the before, then we're going to try to sample the next one. And then we go ahead all the way until the end of the sentence or the end of sequence token is sampled. This is great. It works amazingly well. Nowadays, in your phone, as long as you use Android, because I'm not sure about the iOS, but yeah, if you use Android, in fact, this very same model is being used. And then it's not only by the Google, but if you use, let's say, Samsung Galaxy 9 or 8 or something, then you're going to have the neural net trained by the Samsung people. And then this is precisely the modeling paradigm they use for generating translation or doing the speech recognition or even doing the autocomplete when you type something. Although this morning, Chris told us that the decoding is not a problem, I think still there are some questions that we need to answer. First of all, we actually don't know how to do the exact decoding. Well, because it's intractable, the state space is going to grow exponentially as the length of the sequence grows. And then, as you can all guess, the exponential growth is not that great. And then there isn't much of the structure that we can exploit to write a Bayesian algorithm. So if we know that the size of the state is finite and discrete, and then if we assume some Markovian, let's say, properties, then we can use the Viterbi algorithm. But we don't really have that kind of thing. Or if everything was continuous and linear, we could use the forward algorithm or the Kalman filtering, but that's not true as well. And even if we can solve approximately this problem of decoding, the issue is that it's very, very sequential. So as we want to generate a long sequence, the time it takes to decode that out is very, very slow. So how can we avoid these two issues? It's pretty straightforward, right? So the thing we can do is that we can actually try to say that, okay, there's absolutely no dependencies in the output tokens. So we're going to say that, okay, so the token at the time step t, we can predict it without looking at all the other tokens, only looking at the input source. In this case, we can do the exact decoding because there's no dependency. It just becomes a sequence of the classification problems. And then decoding can be done in a distributed manner in a parallel way. So it's really straightforward. So we're going to start from some input. We're going to feed it to some kind of neural net. I'm not even going to say which one, but you already learned what kind of neural net is going to go in here. And then given that I'm going to just decode out, let's say, the first one, second one, third one, fourth one, all simultaneously. This is kind of too good to be true, right? So it doesn't work. So if you're trying to train a neural net or the machine translation system that you just learned this morning without putting in those dependencies, you'll see that it horribly, horribly fails. And I know because I actually tried. And everyone tries because everyone makes a mistake when they implement it, right? So this is the thing that everyone makes a mistake. Or at least all my PhD students make the same mistake, including myself. Now, how can we avoid this? So let's try to think about modeling this sequential or the temporal dependencies in the output, not in an auto-regressive way, but by introducing a latent variables. So from yesterday's lecture and then a few of the lectures before, you all learned about the probabilistic graphical models. So we're going to approach it from the probabilistic graphical model perspective by introducing some unknown latent variable z. Now, if we have some kind of latent variable, that latent variable is going to capture or try to capture all the dependencies in the output. And then all we need to do is we're going to say, OK, given some input, we're going to infer what this latent configuration is. And then given the latent configuration, which corresponds to the specific types of the dependencies in the output, we're going to try to generate the target. Now, all we need to do is then we try every single possible configuration there. That's going to be marginalization. That's great. Of course, we can never solve that, unfortunately. Just like the same problem as the configuration, number of configurations is a latent variable, will have to grow exponentially. Otherwise, it's not going to be able to capture all those possible dependencies. However, it turned out late last year, that the Jiatao and his colleagues back then in Salesforce proposed that if we put certain type of the interpretation or impose some kind of interpretation on the latent variables, we can train it in a tractable manner and then make it work. So what was it? What was the, let's say, interpretation or the constraints they have posed? So first of all, what they said is that this latent variable is going to be also a sequence. So it's going to be a sequence of some unknown tokens. And then the length of this sequence is going to be same as the length of the source tokens. So that's going to be let's say length of z is length of x. And then each of the token in this latent sequence z is going to correspond to how many times the source token is going to be repeated in the translation or in the target language. If you think about translation, and then if you think about the two similar languages that share the word orders, then it's largely simply deciding, okay, whether this specific word is going to be translated into the target language using 1 word, 2 word, 3 words, or 0 word. So what they are saying is that, okay, let's forget about what the latent variable is going to do. What we are going to say is that given this source sequence, trying to infer for each token how many repetitions we need to put in the translation. And then say if it was, let's say, 1 and 3, then we're going to make let's say, 1 copy of the first token and 3 copies of the second token. And then that's going to work as the template from which the translation is going to be generated. And then how do we generate it? We again use all those, let's say, neural sequence models that you learned. That is, we're going to put it into some neural net. It really doesn't matter whether you use recurrent neural nets, transformers, or convolutional nets. We use transformers here, though. And then just turn each of the token into the target token. It kind of sounds like it's not going to work well, right? I know. I agree with you. But even then, this is a very, very difficult problem. because we need to be able to marginalize out these number of repetitions per source token. And then that space is gigantic. So it's not that easy to train this model. So instead, what Gu et al. In 2018 iClear paper, so earlier this year, what they did was to use the external word alignment model. So they're going to run the word alignment model separately, and then trying to figure out for each of the sentence and then each of the source token how many times it was repeated. And then to, getting the word alignment is actually super easy these days, thanks to Chris Dyer. So there is a package called Fast Align. You can just git clone this and then run it, and then it's going to run like this. And then you can always easily get the alignment, and then these repetitions. Still, it doesn't look like it's going to work well, right? That's what I thought as I read their paper. But then I went to the experimental section, and then their paper showed like the very, very first convincing result that we didn't have to do the auto-regressive modeling for the language generation or the translation. So this is on a relatively small corpus called IWS-LTIS 2016, and then we're going to go from the English to German. So the first two rows correspond to our usual model. So those are the close to state-of-the-art model using the auto-regressive modeling. So that is a token in the target is going to be conditioned not only on the source, but also on all the previous tokens that have been generated. And then if you use the beam search, which has become the de facto standard, then we get a BLEU score of up to 30. And then BLEU score is an automated measure of the translation quality given the reference translations. It's not the perfect one, but this seems to be the only one that kind of makes sense so far for the automated evaluation. And then the remaining three rows are correspond to the approach by this Jetta Gu et al. Yes. So this is non-autoregressive. So what they are going to do is that, okay, given a source token, or source sequence, trying to get a sequence of repetitions, and then do the translation simultaneously. And then what you get is that, okay, these are some different, let's say, techniques, but eventually you could go up to, let's say, 28.16 BLEU score. And then the difference is about 1.5 BLEU scores, and then, like at that point, you can't really tell the difference that much. But one really interesting thing is that how long it takes to translate one source sentence has drastically dropped. So it takes less than half of that time it was taken by the auto-regressive model to translate one source sentence. So that was actually the good thing, right? So we talked about the weakness of the decoding in the auto-regressive model, and that was that it is inherently sequential. So if the sentence is long, it's going to take as long. On the other hand, non-auto-regressive models don't really take that long, right? It doesn't have to, because we can do everything simultaneously in parallel. So this is great, convincing, but at the same time, it's really difficult to implement this. If you read a paper, in order to make this work, they had to put a lot of tricks and then techniques in order to make this model work. And then it wasn't really clear which one was really the factor that made it work. So we decided to look at it from the scratch. So, okay, we are going to start from the Latent variable model, so as usual. So we're going to have some Latent variable, and then it's going to be a sequence as well. But now let's try to impose different type of interpretation. First, we're going to say that this latent sequence Z is going to have the same semantics as the target sequence or the translation. That is, it's going to be a sequence of tokens, and then those tokens are going to be the tokens used in the target language. And then we decided to say that, okay, there are going to be multiple such sequences. So before, there was a source sequence, and then one sequence of Z's, which was a sequence of repetitions, and then that was enough to generate the translation. But what we are now going to say is that there's going to be many such latent sequences. And then based on all of those, we're going to get the translation. And then we can now write it in this way. So we start from the input. We get the first latent sequence. And then, given the input and the previous latent sequence, we're going to get the next latent sequence. And then we repeat it until the very end when we're trying to look at the source sequence and the final latent sequence in order to get the translation. An interesting thing you see is that all these iterations look almost exactly the same, right? So then what we can do is we can use a single neural net to model all these iterations. And then we're going to just share that one neural network. And then the generative story is pretty nice. The generative story is that we're going to iteratively refine the translation over and over until it becomes really nice translation. So what we do is that we're going to first generate an intermediate translation. So we're going to start from some input. So this sequence can be, again, source language or anything like an image or something. We are going to start from that. We generate a very rough translation. So we're going to generate a rough translation. And then given that rough translation and the source sentence, we're going to refine it. And now once we refine it, we can actually do it again. We do it again and again until we see that the translation is good enough or the translation has converged. So it's a very straightforward idea. So you can see that, okay, what's the difference from the autoregressive models decoding is that we are not doing the sequential decoding anymore. We're doing the parallel decoding. So we're going to try to generate all the tokens simultaneously. And then given that translation or the candidate, we're going to try to refine it over and over until we get the good translation. So the reason why we need to always have this kind of nice generative story and the nice interpretation of the Latin sequence is because once we have that, we naturally can derive a learning algorithm. And in this case, we have two scenarios, or the two, let's say, criteria that we can use. First criteria is simply end-to-end training. We're going to start from the X, the source, and then generate the first translation. And then given that, we're going to refine it, second translation, so on and so on. We're going to run it all the way. And then what we do is, at every time step, or every time step of refinement, we want the rough translation to be similar to ground truth translation. So we are imposing that this model needs to make as good a translation at every possible, let's say, refinement steps. And then this is kind of necessary because otherwise the neural net can do really weird stuff. It can try to generate some random stuff until the very end where it tries to create the translation. So instead what we're going to do is we're going to encourage it to, okay, get closer to the good translation at every iteration. So this is the first strategy. The second strategy or the second criterion is conditional denoising autoencoder. Is anyone familiar with the denoising autoencoder here? Generally slightly older folks, right? Yes, I know. So denoising autoencoder is one of the simplest form of the neural net, unsupervised neural network, where the goal is to take as the input noisy version, and then trying to denoise it, get the clean version. And it was all the rage. Denoising autoencoder was all the rage until 2012, when we realized that we don't really need them for training a object recognition model. But then, few interesting things we have learned few interesting things during that time. For instance, if you look at the paper from Guillaume Alain and Yoshua Benjo in 2013 and 14, what we see is that the training this denoising autoencoder is equivalent to estimating the score function of the data generating distribution. Now, what is a score function is essentially the gradient of the log of the p of x, where the x is going to be the actual data points. And then once you train a model, let's say you train a model on the training examples that are from this spiral, then what we get is this kind of gradient field. Denoising autoencoder is going to find the direction toward which the better and better model can, data or the points can be found. So if you start from somewhere around here, if you fit that data points into the denoising autoencoder and then clean it up, then we're going to get closer to the actual data point. And then we can do it iteratively until it converges. Then that is essentially doing the hill climbing in the data distribution space. What it means is that we can now make a conditional denoising autoencoder. So conditioned on the X, let's say source sentence, trying to refine it over and over. That is, refinement is going to be, okay, trying to get the noisy version of the target and then trying to get the clean version. And then if we apply it over and over, the translation is going to get better and better. Now, okay, so this is not really well proven in the case of the discrete, let's say, random variables. It kind of works in the continuous random variable only if you look at the proof. But empirically, we have always known that it works for the discrete cases as well. So what it means is that how we are going to do is we start from the ground truth reference translation, and then we corrupt it. So we're going to add some noise. And then what kind of noise corruption function we use is very much up to designer or the designer of the algorithm. But what we use is we're going to, let's say, randomly select a word, either drop it or replace it with some other word, or let's say swap the order of the pair of the word, consecutive words, or make some repetitions.
Excuse me? Here.
Oh, yeah.
Can you go back to the last slide?
Yes.
Maybe can you explain here again one of those arrows? Is it how one of the instances moves if we feed it once through the fixed autoencoder?
Yes. So the arrows correspond to R of x minus x, where the x is going to be the input to the denoising autoencoder, and then R of x is the output of the denoising autoencoder.
So why doesn't it move one data instance directly to the spiral?
So it cannot really move at once. So it's learning just a score. So how much further it can go is going to depend on what kind of noisy function you're going to use and then what kind of learning algorithm you're going to use. But what it learns is that the R of x minus x is going to point toward the direction where the probability of the data is higher.
Okay.
Okay. So yeah, this is good. Yes, ask a question. Yes. And then, given this noisy version, we're going to fit this noise version together with the input to make the neural net output the cleaner version. So the training is pretty straightforward. We corrupt it, feed it through the neural net, so one of them, right? So one of them, and then trying to ensure that the outputted version or the refined version is going to be closer to the reference translation before the corruption. So what we end up with two different criterion. One is the latent variable model criterion, that is the end-to-end learning, and then we have the denoising autoencoder criterion, that is at every time step, every iteration, the network needs to know how to clean up the noisy version of the translation. So how do we mix it? There are many ways to mix it if you have many different criteria, but in our case, it turned out that it's best to use a mixed or the So, okay, I have to use it. All right. All right. So what we do is we're going to, given an input, we're going to feed it through these multiple iterations of the refinement. And then we're going to train it. But at each iteration of the refinement, we're going to toss a coin. And then if the coin lands head, we're going to say that, okay, we're going to do the denoising. Otherwise, we're going to say, okay, just continue with the end-to-end training. So it's quite straightforward. So at every iteration L, we're going to use either the, denoising or the end-to-end training with a probability alpha L. And then we train everything from scratch. There's really nothing else, so no other cost function or objective function or no other regularizer or anything like that makes things, let's say, complicated. This is the only objective function we have, meaning that as we heard in the morning, you can just take whatever the framework of your choice and then implement the whole thing, just write the loss function and then dot backward, and then it's going to do the training. So we tested on the various translation problems. First one was the low resource machine translation problem with the Romanian. So we're going to do the translation from English to Romanian and also Romanian to English. What we see, so the first two rows, as usual, as before, is the auto-regressive baseline. Those are really good numbers. So we get up to, let's say, 32 blue scores both directions. And then it takes on GPU about, it can translate about 40 source tokens per second. It's a very naive implementation. If you use, let's say, I think the Marian NMT is probably going to be like 4,000 or something. But let's say if you implement it very naively, you're going to get up to, let's say, 40, let's say, tokens a second. But then, if you use the proposed non-auto-regressive model that does the iterative refinement, we can, in fact, control how much refinement we're going to do in the test time, and then see that as we let the model refine further, all right, as we refine further, the score gets higher and higher. And then what happens is that we can, in fact, just stop the refinement automatically by looking at whether the translation has converged. And what we see is that we can actually get up to about 92% of the translation quality while achieving the 4x decoding speedup on GPU. Because again, everything can be parallelized. And then the number of iterations or the number of refinement iterations does not have to be as long as, or does not have to be as many as the length of the source sequence. We tested then on the English-German, which is a bit of a modular scale machine translation data sets. So it used to be a large scale, but not anymore. It's very modular scale, even low resource these days, right? And then on the auto-regressive side, we see that so if you go from the English-German, you get the blue score of 25. If you go from the German to English, you can go up to, let's say, 29. And then these models can translate about 45 source tokens per second on average. And then if we use the non-auto-regressive model, similar to the before, as we iterate more and more, we get better and better score. And then ultimately, we can go up to about 80% of the translation quality of the auto-regressive model, however, with up to or more than 2x decoding speedup on GPU. Now, the interesting thing about this non-auto-regressive model is that we can make a very natural trade-off between the quality and decoding efficiency. So as we take more and more number of refinement steps, the performance or the translation quality almost increases monotonically, kind of confirming let's say, our use of the denoising autoencoder criterion as estimating the score function. But we can always stop at any point. So if you're, let's say, deploying this translation system for a real-time conversation, you want to minimize the latency, then you're going to just let the model do a very few steps of the refinement while sacrificing the translation quality. But if you're going to use it for document classification or some kind of offline translation, you're going to use as many refinement steps as possible in order to get the maximal translation quality. And the interesting thing is that it's all parallel. And I wonder if this is what a human brain does compared to the auto-regressive model. But I'll let the neuroscientists figure that out. So let's take some of the examples. So we're going to start from the German source sentence. And then this is a reference translation. So some of my German-speaking friends told me that this is a pretty lousy translation. But let's just stick to this. And then we start from the source sentence. The first translation is quite rough, especially if you focus on this underlying parts. That underlying parts doesn't really make any sense. It really doesn't make any sense. But as we let the model refine the translation over and over, it gets better and better. And then it gradually becomes understandable translation. And eventually, we see that that underlying parts evolved into the correct translation. And then we see this kind of behavior for any kind of source sentences that we tried. So this is a second example, again, going from the German to English. And then we see that, especially the interesting thing is that in this case, it starts with, let's say, was pretty unsure, though, which doesn't make any sense. But it gradually adds in the necessary words that were missing in the first, let's say, few steps of the iterations. The nice thing about these neural nets is not that we can train it and then we get a good score. The good thing is that as soon as we can project any kind of input into the continuous vector space, we can do whatever we want. So the very same technique we thought or we wanted to build for translation can be used for image caption generation or whatever. So we decided that, let's try image caption generation. This is a pretty lousy task to start with, but it's a fun problem. So as usual, the first two rows correspond to the auto-regressive baseline. The blue score is not a good metric in this case, but roughly it tells us whether our system is able to generate something sensible. And then in this case, on GPU, it can translate about one source token, or the image in this case, yes, one image per second. On the other hand, if you use the non-auto-regressive model, the one that we proposed that uses the iterative refinement, then we can go up to 85% of the caption quality according to the blue score, while getting up to 5x decoding speed up on GPU. So what happens in the image caption generation case? So we're going to start from this image. And then first description is, again, pretty lousy in terms of the syntax. So it does have all the, let's say, necessary content words. But if you read the caption, it really doesn't make much sense. But as we let the model refine over and over, eventually it does get a very sensible and well-formed description of an image. Similarly, if you look at this image, our model is going to generate, again, kind of makes sense because you see those content words, right? So there is a bus, and it's parked, and then there's a bit of a yellow, and then there is probably a parking road or parking lot. But then, as we let the model refine further and further, it actually starts making a well-formed description. And then eventually, it actually does make a pretty decent description. So that concludes the part one. So what do I want to say in the part one as a conclusion is that introducing these latent variables allow us to capture output dependencies without having to resort to the autoregressive model. And then interestingly, different interpretation of what those latent variables are lead to different learning as well as decoding algorithms. So Giotto Guerrero, so Salesforce team, imposed that the latent sequence is going to be a sequence of repetitions of the corresponding tokens. And then they ended up with the auxiliary supervision based on the extra, let's say, external word alignment, plus the noisy parallel decoding. On the other hand, we impose that these latent variables are the intermediate translations that need to be refined, and then we ended up with the conditional denoising. And then there are a few other works, such as the one from the Google Brain recently, show that they impose that the latent sequence is going to be some arbitrary sequence, but the length is going to be always shorter by some, let's say, multiplicative factor than the source sequence. And then they ended up with some weird hidden autoregressive inference model with some, let's say, difficult to understand learning algorithm. So generation quality closely tracks the autoregressive models, but if as you saw, they're still far away from it. One nice thing is that the decoding is significantly faster, especially with GPU, because of the parallel nature of the computation. And then probably this model is going to gain more efficiency if you use a specialized hardware. So some of the future directions in this work include mix of the non-autoregressive model and autoregressive paradigm. So you can think of this refinement as some kind of post-editing. So you're going to be given some lousy or some reasonable translation. And then what you want is that you don't want to break the entire thing and then get the new translation, but you want to just refine it a little locally. So that is very much connected to the recent work on the using neural net to do the automatic post-editing. And then some of the work, such as the Google Brain one, as well as the Wang et al. From this year as well, they actually mix in the autoregressive, non-autoregressive modeling. For instance, autoregressive model is going to generate one segment, the sequence of segments, and then each segment is going to be turned into a tokens, natural language tokens, in a non-autoregressive manner. And then there are many possible ways, and then we think, like this might actually help us go beyond the sentences and then try into the generation of the paragraphs or even the documents. A lot of exciting future directions. So yeah, let's get some questions for the part one, and then let's move on to the part two. There was a question there? Yeah.
During the iteration of decoding, can the system increase the sequence length, the target sequence length?
That's a very good question. The question is that, okay, can the system increase or decrease the target sequence length? And in fact, the better question would be, how does the system decide on the length of the target? I didn't mention that, right? So in the autoregressive model, it's very natural because we're going to let the model generate until it generates the end of the target sequence. But in this case, we don't have that. So what we do is we train another model simultaneously that's going to look at the source sentence and try to figure out what the target sequence should be. And then we use that sequence. And what we do is we're going to add slight epsilon. And then what can be done is that this model cannot increase the length, but it can always shorten the length because it can always generate end of the sequence in the middle, and then we can always chop it out. Right? So that's what we do. Is there any other questions?
I had a question.
Yeah.
So perhaps I missed this, but could you share some intuition into why adding some noise and denoising it is helpful? And also, what is the significance of stochasticity, as in with some probability you denoise and then with other probability you don't?
Right. So, okay, so there are two questions. The first question is that why do we have to, okay, so not this, okay. Why do we have to add the noise, right, when we do the denoising autoencoding? So this actually is quite straightforward if you look at this example, is that what we want what we want to do with the denoising autoencoder is that we want denoising autoencoder to be able to push the points that are slightly off the data manifold, that is, where the probability is really concentrated, in toward this data manifold. That is, we're going to start from one of the data points here. That's going to be a training example. We add some noise so that it's going to go off the manifold. And then denoising autoencoding, so training it to denoise, is effectively learning to push it back. That's why we get all these gradient toward the data manifold. So that's why we have to do that. And then okay, so there was a denoising autoencoder, and then here. And then, so why do we have to do this kind of stochastic mixed training? So I don't think we have to do that. But what we found was that this kind of mixed training objective helps us minimize, somehow minimizing the computational efficiency. So it doesn't really help that much. And also, what we want is that we want our model to be robust to two things. One is that we want it to be robust to what kind of output or the rough translation it gets from the previous layer. And then second thing is that we want it to be also robust to any kind of noise near the actual translation. And then so what we want is that we want our model to be robust to one of those type of thing without knowing exactly what's going to happen. That's why we did the stochastic thing, but I don't think it's that necessary.
Thank you. So if I understand it right, the first part, what you're doing while denoising is sort of learning this manifold or learning the direction in which to move the data points.
Yes.
To learn them. Okay.
Yes.
Thank you.
Precisely. So let's take one last question.
In the examples that you showed, in the first, before the iterations, like the first sample from the target space, it looks like even though the translations might not be very good, the basic word order of the language is still preserved. Is that possible if they are sampled completely independently, those tokens?
So they are not really well, let me see. I don't think I actually put an example here. So one thing is that because the language pairs that we tried, for instance, let's say English-German and the English-Romanian, the word orders differ, but not that significantly. So I think that is one of the reasons why we do get reasonable translation already from the first iteration. But of course, that doesn't really explain in the case of the image caption generation, because in the image it's a two-dimensional grammar. So what is the word order, right? But then still, it does work okay. And I believe that is because all these neural nets that we have, they cannot really capture the dependencies in the output directly, but it can make the distribution as sharp as possible. So it can actually decide largely, roughly in which location the target token should be, which target token should be. Okay, so that was the first part. And then this one was rejected from ICML, so let's see how it goes. And then the next one is going to be another paper submitted to the same conference. We'll see how it goes, but it's going to be more about the multilingual translation and doing meta learning to do better. So if you want to take a look at the manuscript, just email me, I'll send you that. I'm not supposed to upload it somewhere, but I think I can email people. So we'll see. So this one was done largely by the Jiataogu, Yongwang, and Yun Chen from the Hong Kong University. I just work with them together. So what is multilingual translation? So multilingual translation is like one of the, I think, most fascinating problems in machine translation and natural language processing. That is, we want to build a system that translates not from one source language to one target language, but from, let's say, some n many source languages to n many target languages. So traditionally, before the neural machine translation, what people have been doing is that if there is a parallel corpus between two languages, they're going to just build one system for each direction. So they're going to build one system for going from source to target, the other system for going from target to source. And then often what happens is that there are many language pairs where you don't have any kind of direct parallel corpus. That is, like there is no, let's say, document that was translated from one language, language A to language B, unfortunately. In that case, what people have been doing is so-called pivot-based translation. So you're going to translate the source sentence into one of the intermediate language, and then from there, you're going to translate it into the actual target language. Well, I thought it was often English, but I've been told by a lot of people that English has not been the pivot for a lot of language pairs. So it largely depends on which language pair you're talking about. But in these cases, one thing that is really unsatisfying is that there is almost no knowledge transfer between different language pairs. What we want, instead, what we want is that we want to be able to build a system that is able to exploit underlying regularities across many different languages so that it can translate between two languages where we have very, very low amount of data. And then fortunately, from 2015 and on, we learned that these neural machine translation systems can help us. Why is this the case? As you learned this morning, and then in the first part of my talk, is that this neural translation system is going to look at the source sentence and then project it into the continuous vector space. And then once the projection is done, the decoding part, so the language model part, never sees how the source sentence looks like. It really never sees that. The only thing that it sees is continuous vector representation. What it means is that if we can project source sentences written in multiple languages into a single shared continuous vector space, from there on, we can translate it into whatever the language we want. It doesn't really matter which source language the sentence was written in. And then this was done since 2016 by my collaborators as well as the team in Google Translate, Karlsruhe, and then also at NYU. So there are two ways to go for it in the multilingual translation when we view it as a multitask learning. So the first thing we are going to do is we're going to build one encoder for each source sentence and then one decoder for each of the target sentences. And then what we get is we're going to combine one encoder and one decoder, plug them in, and then consider it as one neural net, and then train it with the corresponding language pair. And then let's say if I have another language pair, example from another language pair, I'm going to pick one corresponding encoder, corresponding decoder. I'm going to just plug that in, tune it. Because the neural nets are at the end of the day just like Legos, right? So we're going to build all those blocks, we're going to plug in. And then as long as the dimensionalities match, we can always use different blocks in however the way we want. So that was 2016, together with the Oran Fira, who is now at Google Translate. We worked on this, and then it worked kind of okay. But then, immediately afterward, we realized that that's not even necessary. We can have a one neural net as long as we know how to project each word or the token in different languages into a shared token. Once we have a shared token, neural net doesn't really care, right? What neural net looks at is just a sequence of one-hot vectors. So then, who cares? Neural net is going to figure out what kind of language the source sentence is written in, and then does the translation. So that's the work by from the Google Translate, Karlsruhe, and then also the people at NYU working together with me. That's actually Jason Lee from the previous work. And then all we need to do is find this function that maps whatever the token you have into a shared vocabulary. And then once you have that, all you need is just one single neural net that does the translation between any of the language pairs that you can think of. And the training is easy. We just do the SGD with using all possible resources. So together with Jason in 2017 and 16, what we did was that we realized that we don't even need this function if we carefully choose the languages. If you use, let's say, all those European languages, they all use the same set of letters. So we decided to build a character-level translation system, and then that's going to be also multilingual. So we built a system that's going to translate from any one of German, Czech, Finnish, Russian into English, and then compare it against building 4 different systems that translates from German to English, Czech to English, Finnish to English, Russian to English, respectively. The latter model, the multilingual system, obviously has the quarter of the parameters. But then, when we tested it, looking at the blue score, we see that the multilingual systems are better in general, and especially better for Finnish to English. And even in the human evaluation, when we looked at both fluency and the adequacy, the multilingual system was significantly better than the single pair systems. That was good, right? So that's really great. And then this is actually awesome, especially because we don't have to tell the neural net which language the source sentence was written in. All we need to do is we just give a sequence of one-hot vectors to the neural net, and it's going to do its best to the translation. So one example we did was to make a source sentence with a code switching. So that is, this is going to be a sentence where it starts with one language, switches to another language, switches to yet another language, comes back to the original language, and so on. So in this case, we start with the German, moves to the Czech, back to German, goes to Russian, and then back to German. And then we give it without telling the neural net which language each part of the sentence was written in. And then the neural net was able, this specific multilingual system was able to translate it into English pretty much perfectly in this case. So this is good, but of course, everyone only talks about how awesome these multilingual systems are. But I'm going to talk a bit about the limitations. So the first limitation is that it's extremely tricky to train this model. It's not at all easy. Especially if the resources you have for different language pairs differ significantly, it becomes more of an art than science. You need to know how to schedule them really carefully, how to always stop the training, and then how to oversample the low resource language pairs, how to undersample the high resource language pairs. It becomes a bit of a really horrible thing to do. So, and then, if you are interested in read this paper and that paper, there are just 2 paragraphs describing that because nobody wants to say that and then no reviewer is going to like it, but it's a pretty horrible thing. And second thing is that it actually assumes the availability of all language pairs in advance. And then whenever there is a new language pair with a very small amount of data, we will either have to retrain the whole thing or do some kind of fine-tuning. In fact, recently there were 2 papers on doing the transfer learning, that is, fine-tune the existing system on the new language pair to do better than training from scratch. But if you read those papers, then you realize that in fact, we actually don't know how to do that. So this is one table from the Zofel 2016. So they train one translation system, and then they're going to fine-tune it on the target language resources in order to make it work better on the target language. And then they were like, okay, what should we do? Let's retrain only the source embedding. Maybe we should retrain the recurrent neural net on the source side as well. Maybe we should fine-tune also the target recurrent neural net. Maybe we should fine-tune the target attention. Or maybe we should fine-tune the target input embedding. Maybe fine-tune the target output embedding. And they tried every single one of them, and then one of them was better than all the others. And then the thing is, this is going to change from one language to another, which source languages you use, what kind of model you use. So essentially, we don't really know how to do that. Although it works, but it's, again, art more than a science. So there are a number of inconvenient truths. I just talked about most of them. The last thing that I didn't talk about was that, okay, so how do we know that the parameters you get from the multitask learning or the multilingual translation is good for fine-tuning? We actually don't know. We just hope that that's going to be the case, but who knows? Maybe not, right? So it seems like it's not really satisfying, and then we've been talking and thinking a lot about how can we do it in a more satisfying way. That's when we read the paper by the Chelsea Finn and others from the Berkeley and OpenAI on the meta-learning, or the more specifically model-agnostic meta-learning called MAML. So we're going to train a neural net. So okay, this part becomes kind of confusing. I'm still confused myself. So we're going to train a neural net as usual, but we're going to train it in a multitask learning wheel. So you can think of it as we're going to train one multilingual translation system using a lot of different language pairs. And we're going to use the stochastic gradient descent. Now, in the stochastic gradient descent, we do it iterative optimization. So we're going to look at one iteration. In one iteration, there are 2 steps. First step is we're going to simulate learning. So we're going to simulate what's going to happen if we train this model on a specific data for a few steps of SGD. And then in the meta-learning stage, we're going to train the entire network, including SGD steps. Because stochastic gradient steps are also differentiable, you can backprobe through this stochastic gradient descent and then update the parameters. So the first step, simulated learning. So we have number of language pairs. We're going to pick one language pair, and then from that, we're going to collect one mini batch. So we're going to randomly sample a small mini batch. And then we're going to start from the current parameter, take one or some n many SGD steps. We're going to do the SGD on the parameters. And then this is going to be a simulated learning because we are not going to update the parameters at the moment. We're not updating them. We're just trying to see what would happen. So we do the update. And then in the second meta-learning stage, we're going to sample another subset, another mini batch that's going to be used as a validation set. And then the validation set is going to be used to evaluate the updated parameter, theta prime. So that updated parameter is from the simulated learning. So it's not the current parameter, but what would happen if I updated my model using this mini batch? What would happen? And then the interesting thing is that the stochastic gradient descent steps are just like a layer in neural nets. We can backprop through it. So what we're going to do is we're going to try to maximize the performance or minimize the loss or the simulated loss with respect to the current parameter. That is, we want our parameter to be really good, to be fine-tuned on the new data. Does this make sense? Sort of? Yes? So let's look at this figure. That's easier. So this is what we usually do. So we're going to train our model on the very large resource, source languages. Let's say, like French to English, Spanish to English, Portuguese to English. We're going to find the point in the parameter space that's going to solve these problems as well as possible. And then what we hope is that this is a good point to fine-tune toward the new language pairs. But the thing is, okay, how do we know that that's a good point? That's the first question. Second question is that isn't there an issue with the overfitting to the source tasks? So we're not even talking about the overfitting to the training examples. Now we can think of the overfitting to the training tasks. Now instead, in this memo, what we do is that we are going to try to find a point from which we can fine-tune rapidly to find the model that's going to solve these source tasks really well. So we don't really care about the actual parameter or the model that's going to solve these problems. We want to find the model or the initialization that's going to be really good at being fine-tuned. And then, because of that, there is no, let's say, issue of being overfitted to the source language pairs. That's not true. Okay, there is an issue, but there is less of an issue of overfitting to a source task. And then what we hope is that this point, which is good to be fine-tuned, will be useful for solving new tasks, low-resource language pairs. So does that make slightly more sense with the figures? Yes? Yes? OK, at least one person noticed. So that's good. All right. So of course, unfortunate thing is that we cannot really use it directly for the language translation because the memo assumes that the input and output, so the input and output are same across all the tasks because we need to have the same set of parameters. Essentially, it's the same neural nets. But in the case of the translation, we have the different vocabularies for different languages. So we had to overcome the fact that there is a mismatch between the input and output across the tasks. So what we did was to use the multilingual word embeddings that were proposed recently by the Mikel Artese as well as the Alexis Kono and others. And then what we do is we're going to use the many monolingual corpus to find the multilingual word embeddings that are going to be shared across all these different languages. And then we project it into a multilingual embedding first, and then do the translation. Now that allows us to apply the meta-learning or the memo to the language translation. More specifically, we use the technique of the universal lexical representation by the Giotto Gu et al. Back then, Giotto was doing internship at Microsoft Research. So experimental results is quite straightforward. So we took all those languages from the Europar. So we took, let's say, Bulgarian, Czech, Danish, German, I forgot, and all those languages you can think of. And then we added Russian. What was EL? Greek, yes, Greek. Okay, yes, Greek, Spanish, the Estonian, something, right? And then Russian. So those are all reasonably high resource language pairs. And then we have the 4 kind of simulated low resource language pairs: Romanian to English, Latvian to English, Finnish to English, Turkish to English, and Korean to English. We're going to use approximately 16,000 target tokens, so English side target tokens, which corresponds to roughly about 800 sentence pairs per target languages. And then, as I said earlier, we use a universal lexical representation obtained from Wikipedia. And then this meta-learning is also SGD, right? So we need to have the validation tasks to do the early stopping of the meta-learning as well. And then for that, we tried either Romanian to English or the Latvian to English. And then we actually do see that the choice of the validation task actually matters. So this summarizes the overall results. So the first two bars, yellow and red bars, correspond to multilingual translation plus followed by the transfer learning. On the other hand, the purple and blue bars, the second two bars, correspond to the meta learning plus fine-tuning. And then what we see is that across the language pairs and then across the different ways of doing the fine-tuning, the meta learning based approach significantly outperforms the multilingual plus transfer learning approach. And then are they actually significant? It's kind of difficult to see, but these are error bars there. So we tried it for at least 5 times for each of the languages, and then what we see is that the variance is actually pretty small. And then the meta learning almost always helps. And by doing so, using only about 800 examples, we get up to 65% of the fully supervised models, which were using about 100 to several thousand times more training examples. So what are the things that we found is that the more source tasks helps, clearly, for most of the languages except for Korean. I don't know what's going on with the Korean to English, but this actually suggests that there is some kind of dependency on the source tasks itself, because most of the source languages were European languages. On the other hand, Korean does have a quite significant, quite different, let's say, grammatic structure as well as the lexical, let's say, structures. And then what we see here is the most interesting part, from my opinion. So you can forget about what the solid and the dashed curves mean, but if you look at the red and the purple only, so the red one is from the meta learning, purple one is from the multilingual training followed by the transfer learning. What we see is that in the case of the multilingual translation followed by the transfer learning, as we train the model more and more, the fine-tuning quality degrades because it actually overfits the source tasks. The model itself becomes better at solving the source problems, but they are not, the parameter is not necessarily good for being fine-tuned for the new problem later. But on the other hand, in the case of the meta learning, because that is precisely the objective that we use to train or find these initial parameters, we do see that there is no such degradation, even if we train it longer and longer. And what we see is that the effect of the let's say the advantage of doing the meta learning is especially important when we have a fewer target examples. So when we have only about 4,000 target tokens, which is going to correspond to, let's say, I don't know, 200 training examples, the gap is larger between the meta learning and multilingual learning. But as we have more and more, let's say, training examples for the fine-tuning, the gap decreases, which is kind of understandable. So here are some of the sample example translations, but it's kind of difficult to tell. First of all, okay, I don't speak Turkish, so let's pass. So if you look at the Korean, interesting thing is that before any kind of fine-tuning, the model already does some translation because we use the universal lexical, let's say, representation. But what we see is that the word ordering is a bit off because all the source tasks were European languages with the mostly SVO order. So what we see is that the word order is a bit off. It's just doing the kind of word-to-word translation. But as soon as we fine-tune it just a little, it rapidly figures out that the Korean is a verb final. So when it translates to English, it needs to actually put the verb at the beginning instead of, let's say, putting it always at the end. And then we do see this kind of examples quite a lot, but there are a lot of languages, and then translation system itself is not that great, so it's difficult to do some analysis, but further analysis is definitely necessary. So the conclusion of the part 2 is that, okay, meta learning actually allows us to exploit many high resource tasks for extremely low resource target tasks. Such, in our case, we used 800 training examples for building a translation system, and then it actually worked pretty well. And then at a more high level, what we see is that there is some kind of gradual shift toward higher order learning. So higher order learning is not even a term, I just made it up. But what I mean is that we are trying to actually build, so before, what machine learning, our goal was to come up with an algorithm that's going to solve a problem. But now what we're trying to do is we're trying to come up with an algorithm that's going to come up with an algorithm that's going to solve the problem. So for instance, learning to optimize is one thing that people have been working. So learning is generally optimization in neural net. So can we actually find or machine learn the optimizer itself? Also, there is the huge surge of the interest in the multi-agent modeling. And in that case, can we train a neural net agent to model what the other agent is going to do, or how the other agent is going to learn itself. And there is a lot of work from the Google Brain on the neural architecture search, that is can we find the architecture that's going to solve the other tasks well. And there is the hyperparameter search as well. In fact, hyperparameter search has been very much of the manual labor or the random search, but can we do it better by using machine learning on top of that? And then there are many more on the horizon. So I promised, let's say, 2 lessons that I have learned. First lesson, okay, so personally, I thought, sequential decoding of a sequence was the answer. That's why we worked on the recurrent neural net language model so much. And also, I thought that the multitask transfer learning was the answer to low resource language pairs. And then that's why, again, I spent a lot of time on that before. And in both cases, I was so wrong, I think. So those 2 may not have been the only answers. And then there are many possibilities. And then the thing is that the fact that I have been so wrong is that I will probably be so wrong. So don't take all these things with a grain of salt. And then the second lesson is that it seems like we can actually use denoising autoencoding, or the iterative refinement, for structured output prediction pretty well. And then we know how to train this denoising autoencoder really well, because that's precisely what people have been working on from 2006 to 2012, like nonstop. There was a new algorithm every month. And it seems like the second order learning may become a thing that we can actually use for the practical problems. What it means is that it seems like there are a lot of different learning algorithms as well as the learning regimes that we don't know, that we need to discover. So SGD is good, maximizing the log likelihood is great, but perhaps we need to be more open-minded about trying to come up with a better learning algorithm or the better learning framework itself. And that actually concludes my talk. Thank you. I think I'm probably over time, but there is a question, okay? Sorry, Andre, I'll just take up, let's say, 3 more minutes. Right, so the question is, okay, so why we use the, let's say, multilingual embedding for the meta-learning experiments rather than the character level encoding, which can be actually easier to encode many different languages. So in this work, earlier work, we did use the character level model. This is fully character level, but the character level model also has an issue. So for the European languages and many of the more or less phonetic languages using the phonetic alphabets is actually fine, but there are many other languages that are not. So for instance, in the case of Chinese, the size of the vocabulary doesn't really change much, and then it's unclear, like whether that's the right way to go. Even for instance, for Korean, the character-based representation is kind of tricky. We probably will have to go for the consonant and vowel kind of thing. And then, it's a character level representation is good for the languages that fits with the other languages as well, but there are many corner cases that are not that easy to resolve. Okay. Does that answer your question? Okay, so I guess that's it. Yeah. Summer school is almost done. Except for the closing remark, yes.